In our last buffer gate, it was shown to be very basic, and we will find that just controlling these gates using switches is not adequate, especially when we have multiple logic gates. So we must now introduce a slightly more sophisticated device, such as a transistor. The grandfather of the transistor was the valve, or vacuum tube. The early valves were about 95 to 160 millimeters in height and was powered from a 230-volt transformer. In the early 1950s, the silicon transistor was introduced, which was powered from a 1.5 volt or less power supply and was about 5 to 10 millimeters in height. Now we can find many thousands on top of a pinhead. They are so common, nowadays it's difficult to avoid them. These transistors are the key to the most computerized system, such as RAM, CPU and integrated circuits. There are many different types of transistors, different shapes, sizes, power rating and price. Some are used for power circuits that handle many amps. Some are used for frequencies, others for sound amplification, just to mention a few of their uses. Basically, the transistor has 3 pins: collector, base and emitter. This is a schematic diagram for a transistor. If we do not apply any base voltage, no current can flow between the collector and the emitter. When the voltage hits the threshold voltage, the transistor starts to conduct from the collector to the emitter. Therefore, when the base voltage is 0, it is an insulator, and when the threshold voltage is reached, it becomes a conductor. Hence the name semiconductor. Let's take our last logic buffer gate and convert it using a transistor. Once again, we have to include our current limiting resistors for our LED and also for one of our transistors. We shall again incorporate a switch. In reality, we don't have mechanical switches as the computer relies on logic pulses. What we are trying to prove here is the logic theory, and include our logic table. As before, current travels from the battery and through the 2 resistors R1 and R2, but because there is no base voltage at the transistor, current cannot travel through the transistor and the LED does not light. So we could say when the input is 0, the output is 0. Let's close the switch. This time there is a voltage at the base of the transistor, so now the transistor is in its conductive state. A complete circuit can be made and the LED lights. So when the input is 1, the output is 1. Now let's create a practical version of this on our breadboard. We bring back our breadboard, power supply and our truth table. The first thing we shall look at is the transistor. The model number of this transistor is 2N2222. We can see from its specification that it is an NPN, which is a negative-positive type of transistor. An alternative to this is a PNP, or positive-negative type. These refer to the materials that make up the transistor. We shall look at this in a little bit more detail later, but for time being, to make our transistor conduct between the collector and emitter, we must apply a positive voltage to the base. Once again, it does not matter at this stage where we position the transistor as long as we follow the schematic diagram. Next, we can see that the negative end of the LED is connected to the collector of the transistor. Also, R2 is from the positive rail to the positive side of the LED. Next is a switch, which we can place in proximity to the transistor. Next, R1 is connected from the positive rail to the left-hand side of the switch. We need a link from the switch to the base of the transistor, and finally a further link from the negative rail to the emitter of the transistor. This completes the circuit. So to recap, in our schematic diagram, when the battery is connected, the current flows through both resistors, but because the switch is open, there is no base current and the LED fails to light. With our breadboard connected to a power supply, the current flows to the positive rail at the top. It then travels down the resistor connected to the switch. It also travels down the second resistor, but because there is no base voltage, TR1 fails to conduct, and so the LED does not light. We could say that when the input is 0, the output is also 0. Back to our schematic diagram. This time we close the switch, the current flows through both resistors, and now there is a voltage at the base of the transistor. It begins to conduct, and the LED lights. In our practical breadboard, the switch is switched on, the current flows to the positive. Down the first resistor, current also flows through the second resistor, and to the switch, and to the base of the transistor. Because there is a voltage at the base of the transistor is in a conductive state, and current can flow through it to the LED, causing it to light. We could say when the input is 1, the output is 1.